Dijkstra's shortest path algorithm is one of the classic algorithms for finding the shortest path between two nodes of a graph. It was developed by a Dutch computer scientist called Dijkstra. So here we have a simple weighted graph, and we want to find the shortest path between A and E. With this algorithm, we're going to generate a table of information like this. In this table, we can see the shortest distance from A to every other node. Initially, we assume the distance from A to A is 0, and the distances from A to all other nodes are unknown. So we set them to a large value. As we navigate in this graph, if we find a shorter path, we'll update this table. Let me show you. So we start from A. At each step, we look at the unvisited neighbors of the current node. So the unvisited neighbors of A are B, C, and D. Now we calculate the distance from the start node to each of these neighbors. In this case, the start node and the current node happen to be the same node. That's the A. So what is the distance from A to B? It's 3. We compare this with the known distance to B. That is what we have in this table. Since we have found a shorter distance, we should update our table. So we set the distance to B to 3. Now, how did we get to B? Via A. So we need to record A as the previous node in our table. We'll need this later when we construct the full path between two nodes. Basically, every time we find a shorter path, we need to record where we came from. That is the idea. So let's repeat this step for other neighbors of A. The distance to C is 4, is shorter than what we have recorded in our table, so we should update our table. And one more time for D. We're done visiting the A. Now we look at the neighbors of A and pick the one with the shortest known distance. Out of these 3, D is the closest, so we're going to visit it next. Now we repeat these steps. We look at the unvisited neighbors of the current node and calculate the shortest distance from the start node to each of them. If we find a shorter path, we'll update our table. So D is connected to every other node in this table, but out of these, we have already visited A, so we ignore that. Now we calculate the distance from the starting node to each of these neighbors via the current node. We know the distance from A to D. We also know the weight of the edge from D to B. So the distance from A to B via D is 2 plus 6. Now we compare this new distance with the shortest known distance to B. Our new distance is not less than 3, so we're not going to update our table. The shortest distance to B is still what we have recorded in our table, okay? Now let's calculate the distance from A to C. That is the distance from A to D, which is 2, plus the distance from D to C. Now we compare this with the shortest known distance to C. Obviously, we found a shorter path to C via D, so we should update our table. One more time. Let's calculate the distance from A to E via D. It's 2 plus 5. Obviously, it's shorter than the known distance, so we update our table accordingly. We have visited all the neighbors of D. Now we should pick the closest one and go there. Out of these, we can go to either B or C. Let's go to B. We repeat our steps. We look at the unvisited neighbors of B. That is E. We calculate the distance from A to E via B. That is 3 plus 1. This is shorter than the known distance to E, so we found a shorter path and we should update our table. The shortest distance to E is now 4 via B. We're done with B. Now we need to find its closest unvisited neighbor. That's E. At this point, we have visited all the neighbors of E, so we're done here. The only node that is left is C. But again, we have visited all the neighbors of C, so our algorithm stops here. Now in this table, we can see the shortest distance from A to each node in this table. And using the previous node column, we can build these shortest paths. For example, let's say we want to print the shortest path from A to E. We know we got to E via B, and we got to B via A. So the shortest path from A to E is A, B, E. So this is Dijkstra's algorithm. This algorithm is an example of what we call a greedy algorithm. A greedy algorithm tries to find the optimal solution to a problem by making optimal choices at each step. In this case, at each step, we try to find the shortest path between the current node and its direct neighbors. That's a greedy algorithm.